you begin with, say, indicator function, prove it for indicator function, prove it for non-negative, measurable functions, and then, for general ones actually. So the recipe is same. So I'm not getting into the proof. It's going to take time. So it's a readable proof. Read it for yourself. Something that you know also from your previous courses if you have seen it. If not, see it now. So if x and y are independent and integrable random variables, okay, then the product is integrable. Okay, integrable. Okay, and not only that, but if you integrate x and y, in other words, if you compute the integral of the product with respect to the probability measure, okay, then this must be same as expectation of x times expectation of y. You must go through the proof of it at least once in your life. So not getting the proof is pretty dominant, as I'm saying that, pretty standard in the sense that you take first x and y to be the indicator functions, then you take x and y to be the simple functions, then you take x and y to be, what do you call, non-negative functions. So if x and y are non-negative, you can approximate them by simple functions and apply the monotone convergence theorem so you can, get this identity. So it's a very simple application of it's something that you have done already, so I'm not getting into this. In fact, you can generalize this to the n random variables. In other words, if you have n integrable and independent random variables, okay, then their product is also, integrable, and the expectation of the product of those n random variables would be, equal to the expectation of the product actually, okay. And you can prove that also inductively as well. So in other words, that n equal to 2 case, you have done it. Basis step is this actually. So you just have to show the inductive step. But the inductive step would also follows from here actually. So if you assume that k are, independent, then, the k plus 1, so the product of k plus 1 can be written as the product of k times k plus 1, and then, so the whole argumentation. So in fact, I am interested in a result, okay, which is going to be the combination of this and this result, and you have to help me out to prove that, which says that if, so even you can generalize it even more actually, okay, you can take this result to a very new level. So if x and y are independent random variable, in fact you can prove it, if x and y are independent random variable if and only if for any choice of, for any bounded measurable function, bounded measurable function f, let's say, not only measurable but Borel measurable function that must be bounded. Functions f comma g, which are mapped from R to R, we have this. So the expectation of the product of f of x times g of x is equal to expectation of f of x times expectation of g of x. Okay. In other words, if you take a bounded function, no, that's g of x is y. Why this must be true?
So first, x and y are independent.
Yes.
So the composition of g of x and f of x and g of y are also independent.
Yes.
And then by the above theorem,
Yes.
expectation.
Yes. So it's just a combination of, this result and this result. So we said that if x and y are independent, okay. So the forward side I can prove in this manner that, okay, let's take an x and y and they are independent. So if they are independent, I know that if I compose them with any two Borel maps, they are independent too. So
And so since
then f of x, say for example, if I treat that as u and g of y treat that as v, then by this result,
and so they are bounded also, that's why they are integrable. This.
yes. So you're going to get expectation of uv is same as expectation of u times expectation of v. So you got one side. How about the other side? How about the other side? This would be an interesting fact to reflect upon. Think about it for yourself. So in other words, you have to make a particular choice of f and g. Think about what should be that particular choice of f and g that can work here. Anyway, it's equal to phi of x of t and phi of y of t. Where phi is a characteristic function. Characteristic function, okay. Why this would follow?
So because phi of some x is expectation of.
Because just write it there. What is phi of xy plus t actually? So it's the expectation of e to the iota, x plus y, something like that. Okay? And then, I can e to the iota x and e to the iota y, and then e is a bounded function, so you can apply this result and deduce what you want. These are the small things that you can very easily deduce out of. Now, like you might have proven this result without using measure theory previously. Okay, you can directly also show it from definition. For discrete random variables separately and continuous time random variables separately. But so at the moment we are proving it in a more generic, what do you call, manner. Okay. How about here the thing? How about variance of x plus y? If x and y are two independent random variables. So I know that this is same as expectation of what?
X plus y square.
Okay, so I can say either I can apply the definition or I can use this. Expectation of x plus y whole square. Okay. And then simplify it and keep the previous result, and you will see that this would be same as variance of x plus variance of y actually. Okay. So if you have two random variables, then the sum of the variances is the variance of the sum. Have you heard of covariance?
Yes.
Okay. So what is covariance? So it kind of tells you that how two random variables are related to each other. Okay. Okay. So in other words, are they positively related, negatively related? One is increasing, other is decreasing. What kind of relation? So you can just know it through the covariance. And what is the definition of the covariance? I mean, if you remember, the covariance of xy is basically that on average how much x is away from its mean times how much y is away from its mean. Okay? R, I mean, if you simplify this expression, you can write it that this is same as expectation of xy minus expectation of x times expectation of y. Have a guess. If x and y are independent, what you can say about covariance?
Zero.
Why it must be zero?
Because
You
they both are
can see it
zero.
from here. Since x and y are independent, since this must be the product of x and so we know how to do it. How about if you are computing in general variance of x plus y? Well, I don't know that x and y are independent or not. Then what you can show, okay, maybe you can verify this, that this is same as variance of x plus variance of y minus 2 times of covariance of y, 2 times of covariance of x comma y. So since x and y are independent, if x and y are independent, this is 0, so therefore you get this actually. Yes, something like that. It must be plus. Must be plus. Okay. So then there are simple properties about variance, covariance, for example, in exercise 3.37. So you see, if the covariance between two random variables is 0, then we say that they are uncorrelated and so on and so forth. By the way, since we have proved Cauchy-Schwarz inequality in our function analysis course in a much more general setting. Okay. So if I want to write the Cauchy-Schwarz inequality, for example, in the terms of the expectation, what would be that?
Explain that x and y is less than or equal to x.
Okay, here's the thing. So the Cauchy-Schwarz inequality, for example, for integrals is what? So I know that if I have integral of fg, okay, and I'm integrating it in some sense, then this is less than or equal to, so it's less than or equal to integral of f square 1/2 and g square 1/2. Okay, this would be. So what is inner product on? So I can also treat this as the inner product is less than or equal to the norm times norm. How about in case of the expectation? So expectation is also a kind of an integral. So you're going to say that, okay, so if I have an expectation of xy, which is integral of xy with respect to the probability measure, okay, then this is less than or equal to what is square. So expectation of x square 1/2 and expectation of y square 1/2. Okay. So either we can deduce it from a general setting, or if you wish, you can see the proof from the book as well. Okay. But obviously, you need the assumption as well on x and y that they are square integral. The squares should make sense. Okay. So that's it in this chapter. So what we did in this third chapter mainly, if you see from Thomas' perspective, is that we kind of studied, so we kind of translated the basic probability theory that you know previously in Mesotheoretic languages. Okay, so that was one of the key things. And in this chapter there was also Fubini theorem, but we covered it from past, so we are no more much interested in that. What we are going to do next, not today maybe, okay, we can have just an overview today, but the key thing that kind of, what do you call, the Superman of stochastic analysis is something called, this abstract probability is something called the conditional expectation. So our next lecture will be mainly on describing the different versions of conditional expectation. So we'll start with a very basic, that how to condition. So we know how to condition one event with respect to another event actually. So we know that. And we know what does it mean, and so I'm not getting into that. So what next thing I would like to do is that, can I define the probability, okay, or maybe I can say probability or the expectation. So if I have this, then I can also define in some sense that what is the meaning of computing the expectation. For the expectation you need random variables, but I know that I can use the indicator function. I can do this, I can say that, okay, that's what it means, okay. So I can compute the expectation of indicator function with respect to the random variable, and I would like to show that basically this will break down to the probability, this probability, okay. What next I would like to do is that, what would be the meaning, so replace the indicator function by an abstract random variable. What would be the meaning of the conditional expectation of a random variable with respect to, what do you say, an event actually. Okay, this is what the next thing that we'd like to define. Then we'd like to define that what would be the meaning of conditional expectation of a random variable, but with respect to not a set but a collection of set, for example a partition of the omega. Okay. And then finally we will like to prove the more general case, or discuss the general case, that what is the meaning of the conditional expectation of a random variable with respect to an arbitrary sigma field. So this is what we would like to define. Okay, so this would be, and study the properties of it. So we're going to go this way. So I can go this way, but kind of define things in a much more abstract setting, and I deduce all these as an example. But I like to go this way actually. So it's kind of more intuitive. That you'll see that what is going on. Why the definition? So you'll find the definition of conditional expectation with respect to a sigma field a bit strange actually. But if I go this way, you will see that why we require that definition. Okay. So the conditional expectation is of the central importance in stochastic analysis, in finance, and many things. Okay. See you.